Okay, this is chapter 14. We're going to talk about vibrations and waves. So some vocab you're going to want to know. You're going to want to know what periodic motion is. That would be, an example of a pendulum swinging back and forth, or a mass on a spring that's bouncing up and down. As we're going to find out, waves will have periodic motion as well, like a sound wave, or a light wave, or a gravity wave. All right, simple harmonic motion then is motion where the force that restores the object to its equilibrium position is directly proportional to the displacement of an object. So the examples I gave with the pendulum and with the spring are perfect examples, because if you lower this, if you stretch this spring out, that string is going to have an elastic force and have more tension to pull it up. So it would satisfy that condition of it's going to be directly proportional to the displacement of an object. As the object gets closer to the equilibrium position, there's going to be less of a force restoring it, or pulling it in a certain direction. So simple harmonic motion and periodic motion are very similar and are many times overlapping vocabulary used to explain a certain phenomenon. You're going to need to know what period and amplitude are. So period is the time for an object to complete one cycle of motion, and amplitude is the maximum distance that an object moves from equilibrium for mechanical waves. But we will use amplitude later to talk about things like light waves and sound waves, in which case we're not talking about distance from equilibrium. We're talking about, like for sound waves, since there it's just, you have some highly dense air, and then you have some lighter dense air, highly dense air, and then lighter dense air. Now the amplitude becomes how much pressure is in this rarefaction, I believe it's called, where the air molecules are grouped closer together. Okay, you might remember Hooke's law. I believe we've already covered this in the formula sheet, but it's a relationship between force and the distance that you stretch a spring. So I believe we used this in class already, and we found the spring constant of a spring that I have. But just to remind you of this, you're going to want to be able to use that from time to time in these problems. You're also going to want to remember the potential energy stored in a spring, which is 1/2 kx squared, where x is the distance that you stretch the spring again from its equilibrium position in meters. Let's do an example problem then. This says a string stretches 18 centimeters when a bag of potatoes weighing 56 newtons is suspended on it. Determine the spring constant. So we know F equals negative kx, and we can use that. It's stretched 18 centimeters, which is 0.18 meters, and we know the force that's put on it is 56 newtons. So we'll just solve this for k, and that gives 311.1 repeating newtons per meter. So the next question then is, how much elastic potential energy is stored in the spring when it's stretched this far? So that's 1/2 kx squared. So that's 1/2. We're going to need to do negative 311.1 repeating times x, which is 0.18 squared. And this gives us 5.04. And that's energy. So we're going to say joules. And that's, we can have a negative sign there as well, but we don't really need that because we're talking about the magnitude of the energy here. Next equation you want to know, it's on the formula sheet, is the period of a pendulum. So if you remember the pendulum we had with a bowling ball, what you'll notice about this is that this does not depend on how far back you pull the pendulum. It depends on the length of the pendulum. So this pendulum and let's say this pendulum would have different periods, obviously. This one would be faster, this one would have a longer period because it's got a larger L, a larger length here of the pendulum. And it also depends on gravity, so that means that pendulums on the moon and pendulums on the earth would have different periods. Okay, resonance is a term that I would be familiar with. We're going to talk about this in terms of sound waves. We'll talk about it in terms of light waves as well. This actually explains a lot of phenomena that happens in the world. Okay, it's a special form of simple harmonic motion that adds small amounts of force at specific times that cause larger and larger displacement. So a great example of this would be if you're pushing someone on a swing. If you're pushing someone on a swing, you're only going to push when they're going to start to move forward. So you're going to apply a forward force at specific intervals. And what that does is that increases the actual amplitude of the motion in this case. So a great example is the Tacoma Narrows Bridge. I'm sure you've seen that video. If not, go ahead and YouTube that one. The bridge wasn't built very well. So what happened is the wind was supplying gusts of energy that created resonance, and specifically at the natural frequency of the bridge. So we're going to learn that that happens with sound and light as well. And what happened is then obviously the bridge, started to move too much and fell down. But this resonance happens with sound waves. So you can resonate a glass, like a glass, if you resonate it at its natural frequency. So if you put the right frequency of air coming at this, you can break the glass. You know, we're going to learn also that light waves resonate with different elements in the air. So it turns out that, you know, blue light, it resonates with nitrogen that's in the air, and that therefore the sky is blue because it resonates blue light, and then therefore scatters blue light throughout our atmosphere. So this resonance thing actually has a lot of explanation as far as some of the properties for waves go. Okay, so a wave is a disturbance that carries energy through matter or space. You're going to find out there's a lot of different waves. Some examples would be sound waves. We have light waves. We have surface waves, like from water. Obviously, earthquakes, you know, use wave in the form of, like, basically it's kind of like sound. It's just pure energy, you know, from molecules bumping into one another. So we could do earthquake waves, I guess you could call them, or seismic waves. We could also do gravity waves, which have recently been verified. So we have all different kinds of waves that we're going to study. We're going to start with mechanical waves. So we have 3 different types of mechanical waves. We have transverse waves, like if you grab a hold of a string and shake it up and down, then what's going to happen is the wave pulse is going to move away from your hand. And so what's happening in there, the wave pulse is perpendicular to the direction of wave travel. So you're moving your hand up and down, but the wave travels left and right. So that's called a transverse wave. The next type of wave is a longitudinal wave. An example of that would be if you had a slinky and you compressed part of the slinky and let it go. What happens is the wave pulse that you made is parallel to the direction of wave travel in that case. Like a sound wave would be a great example of that. So this is very similar to a sound wave. So we would call that a longitudinal wave. And the last type of wave then will be a surface wave. And that's where the wave pulse is both parallel and perpendicular to the direction of wave travel. So if you've ever laid in the water, when a wave goes over you, you feel like you're kind of moving in a circle, and that's because you are. The particles in the water here are moving in circles. And those are called surface waves. Okay, so we're going to talk about speed of waves, all right? Now, when we talk about speed of waves, we're just going to be using our regular distance over time, so it's not complicated. But one thing that is complicated, and I highlighted it here, something that's maybe counterintuitive, is for mechanical waves, both transverse and longitudinal, the speed depends only on the medium through which it travels. So for a sound wave, for example, it always moves at 343 meters per second through air. Okay, now if we change the temperature of the air, we can adjust the speed. And then if sound enters water, it's going to increase in speed. And our book has tables of values for these speeds. So the speed of sound through water is going to be faster. The speed of sound through steel is going to be even faster yet. So that is very, very important, that the speed of our waves that we're talking about depend only on the medium. And that has to do with the elasticity of molecules, because some molecules are more elastic than others. So for example, steel is very elastic. So what happens is you make a disruption in like a railroad track, for example, and you hit it with a hammer, that energy pulse gets transferred very quickly because of the elasticity of the molecules in steel. So it travels very, very quickly. Some vocab you might remember about that it's imperative you know is like amplitude. You need to know crest and trough, and also wavelength. We use lambda to represent wavelength on our formulas in our formula sheet. So the wavelength is the distance between two troughs or between two peaks or between any two corresponding parts on the wave. Frequency is one I'd like to remind you of. Frequency of a wave is the reciprocal of the period. And that's going to be important because we're going to use that quite a bit. You might hear this, like you might hear hertz in terms of frequency of a sound, a musical note maybe, or the electric current, the alternating current in your electrical circuit. Radio wave frequencies, light wave frequencies. We're going to be using frequencies to discuss properties of these waves. So be comfortable and familiar with frequency. Now there's a relationship between wavelength, speed, and frequency that's right here. That's on our formula sheet. Turns out the wavelength is going to be equal to the frequency, the velocity over the frequency. This formula comes right from distance equals rate times time, because the distance is the wavelength, the rate is velocity, and the time is the period, which is 1 over the frequency. So therefore you get this formula here. Here's a quick example problem to try. If you want some extra practice, we can go over these answers later. Okay, here are the answers and work to those if you wanted to try those and check. So the next section in the chapter 14 is called waves at boundaries. So we're going to talk about what happens when wave strikes a new medium. First of all, some vocab. When we have a wave striking a boundary, like light, for example, hitting the ocean, the wave that comes in, we're going to call the incident wave. And then the part that reflects, we'll call the reflected wave. Okay, the next thing you need to know is superposition of waves. The principle of superposition says that the displacement of a medium caused by two or more waves is the algebraic sum of the displacement caused by individual waves. So this creates interference. It's the result of this superposition. So we have destructive and constructive interference. Those are the two types. So what destructive interference is when you have a wave that cancels with another one. So for example, with sound waves, you have, like I said before, let me draw this real quick right here. So you have, if you want to cancel a sound wave, for example, say here's the frequency of your sound, you want to match that frequency just out of step so that the high pressure of the sound wave is met with the high pressure of a different source. And when you add those waves together, then what happens is you just get this right here. You just get no rarefractions and no diffractions. You just get the regular, pressure of the air, or all one pressure, and therefore you don't hear any sound. That's what noise canceling headphones do, for example. Constructive interference then would be what would happen if I shift this wave over so that the high pressure regions of both these sound waves matched up. That would create constructive interference. You'd experience a sound that's twice as loud then. And that's what you see here. When two waves come at each other, they add up the algebraic sum, and you see a higher amplitude. The book briefly talks about standing waves and some of these properties. If you were to take a rope, for example, and move it up and down, if two people were to hold it at both ends and move it up and down, you could create a standing wave. And the faster that you make the wave, the more nodes you could get. These points in the middle are called nodes right here. And the points that have the furthest displacement here would be called antinodes. And you can create standing waves, like, for example, in the tube of an instrument, a musical instrument with sound waves. Like I said, you can create these with a rope if two people are holding it at one end. What happens is in a rope, the wave goes down. If you move your hand up and down, the wave's going to go down this way, and then it's going to come back. It's going to reflect off the other person's hand and come back the other way. And so if you just keep doing that, you can match your frequency. You can get these nodes. So it's something worth trying if you want to see what an antinode is. But like I said, a perfect application would be this is what happens in a musical instrument, like a trombone, for example, when you change the frequency. Or a better example would be a guitar string. Okay, waves in two dimensions then have a wavefront. So we usually represent like when we have a light wave, I'll represent that with an arrow, but really it's a wave front. And in fact, the sun's so far away and so big that really that wave front's almost a straight line. But we'll represent that with an arrow going this way when in fact it's actually the wave front that's moving. Okay, quick property of reflection of waves. If we talk about an incident ray of sunlight or of sound or of water, any wave at all, the property that they have is when they reflect off a surface, they reflect at the same angle. And you probably know this from playing pool. If you send a pool ball off one part of the table, it's going to reflect the same angle it hit the table at. So this makes sense to you, hopefully. Okay, refraction is something that maybe you're not as familiar with. It's the change in direction of a wave boundary when between two different media. So for an example, here's a ripple tank of water, and you can see that they have a boundary here, and you can see how the light wave or the water waves change direction. You can see the wavefront going this way, and then as it hits the boundary, it goes this way. But the perfect example of this would be like on Earth, you have the atmosphere of Earth, and if you're standing, here, and the sun's over here, or the sun's down here, for example, then all the light is technically getting blocked by the Earth, but the light that goes up here hits the new medium, hits the atmosphere from outer space, and it bends, it refracts. And so you actually view the sun as if it's over here, when really it's already sunk past the horizon. But you see just a mirage, an image of the sun because of refraction.